Chapter 4 System VVT Methods, Non-Testing. Introduction. Engineers often use the term testing colloquially to mean VVT. Following the VVT definition, testing is a subset of verification and validation, dealing with actively operating the system and verifying or validating it. The term non-testing refers to all the VVT activities which are not specifically testing per se. Requirements Verification Matrix, RVM. A requirements verification matrix is usually composed of the following. Number 1, requirements identification code. Number 2, requirement traceability to higher level documents. Number 3, verification methods to be used. Number 4, stage or stages where verification takes place. Number 5, verification procedure identification code. Verification methods often listed in the RVM are analysis, inspection, demonstration, testing, and certification. Verification by analysis. A system analysis method may be used when other verification methods are not possible. As an example, verifying a system's reliability, or are too expensive. As an example, verifying a system behavior in destructive conditions, or endanger human or property. As an example, test flights outside the normal flight envelope. Based on the following means: mathematical models, simulations, algorithms, calculations, charts, and so on. Verification by inspection. A system inspection method typically includes the use of human senses or simple physical tools for manipulation or mechanical and electrical Gaussian measurements, and may be used when the intent is to show compliance with every simple requirement, when it consists of non-destructive examination of items without special laboratory equipment or procedures, typically in component subsystem and system production phase. Verification by demonstration. A system demonstration method is similar to a system testing method. However, system demonstration is considered a softer approach to the verification process, when the intent is only to generally watch a system accomplishing a certain undertaking with typical operating conditions, and this approach is rarely used. Verification by testing. A system testing method should be considered as the default choice for each entry in the RVM. Naturally, most system requirements will be verified by means of testing. Other verification methods will be selected but only under special circumstances. As a general rule, it is considered the most rigorous verification method. Verification by certification. System certification may be accepted instead of tests based on a verified article which has been proven under similar operating conditions. Such certification must indicate the standard procedure to which the testing was conducted and when, where, and by which organization the testing was conducted. State that the testing was successful, and state the reason why a certification method is used. When a new system is variant of an existing, tested and proven system. When the full verification cycle will be expensive and time-consuming. When there exists a long-term relationship and trust between the system procedures and customers, and often during component, subsystem, and system manufacturing setting.
A hierarchical VVT is used for optimization of the VVT process. The goal of the hierarchical optimization is to improve the VVT plans for the complete system, subsystem, and its components. This optimization is done using an iterative process, or a step process, that links this level to the next level, and so on. By directly linking the requirements, you can reduce or eliminate redundant VVT activities. The result is a lower cost VVT. The hierarchical VVT may be used when the system development process is underway. Once the system development process is underway, the system has been broken into different levels, meaning that of subsystems, and further into components. These are the working layers that represent standalone parts of the final system. It is critical that the connection has been made between the system requirement and the requirements that need to be VVT'd at the different levels. In the illustration on this slide, you can see that system requirement 1 flows to subsystem A and component AA and AB. You can see how the top-level requirement is traced downward to the component level. The RVM for the system, subsystem, and components must be available. Each RVM entry consists of requirements identification, requirements traceability, a verification method, which is how you plan to verify this requirement has been met. This can often be analysis, inspection, demonstration, testing, certification, etc. A verification stage, which is at what point in the process you will perform the verification. And finally, a verification procedure, which is how you plan to do the verifying. These stages will often follow the phases of production and development of the system, subsystem, and components. For example, the definition, design, implementation, integration, and qualification stages. When the process begins, all of the requirements are evaluated at all levels. The result is many overlapping activities. By reducing the redundancy, an optimization is achieved. To explain this another way, each requirement should be reviewed at each level in order to determine which VVT activity can be eliminated or scaled back. The idea is to perform a VVT at the most effective time and reduce less effective redundant VVTs, while ensuring compliance. In the illustration on this slide, the original RVMs are applied to the VVT constraints, and the result is a smaller set of RVMs. There are many considerations to be made prior to optimization. Careful consideration to available funding, hardware availability, testing facilities, critical or safety considerations, and the phase of development under review must be considered and may have an impact on the optimization. The following 7 tips are helpful with carrying out hierarchical VVT optimization. First, component requirements are derived from subsystem requirements, which are derived from system-level requirements. The requirements at all levels are strongly related. The validations of these requirements at the different levels may be similar or redundant. Removing the redundant validations is an excellent way of reducing VVT. Second, perform the VVT activities as early as possible. The cost of rework is always less expensive the earlier the defect is identified. Third, it is much more effective to do VVT at the lowest level possible because there are less interacting parts of the system at the lower levels. It is easier to observe correct or incorrect functionality at the component level than at the system level. Fourth, different methods carry different costs. Costs might be time, money, resources, etc. Get the most out of the VVT by choosing the most effective VVT method. Fifth, test your critical items at all levels possible. If you have a safety risk with a high probability of failure, invest more into VVT for this item. Sixth, conversely to number 5, if you have a low risk, low criticality item, it may be more efficient to only test this at the system level rather than repeating the tests at the component level. And finally, number 7, the VVT optimization plan will inevitably result in some testing costs being transferred from one point to another in the production process. This means that some groups will be asked to do more, while others will be asked to do less. Make sure that this is communicated and agreed to by all stakeholders. The following are 4 advantages to a hierarchical VVT approach. First, you can eliminate or scale down the redundant VVT activities at the various levels. This can greatly speed up your overall VVT activities time. Second, implementation is easy and uses a limited number of experts. Third, reducing the number of tests provides a competitive advantage by lowering the costs of the product and reducing the time to market for the product released. And finally, fourth, by doing the hierarchical VVT approach, the VVT strategy is laid out ahead of time and can be reviewed in its entirety. This will highlight any gaps that may be present in the overall strategy.
4.3.3 Requirements, Testability, and Quality. System requirements must be understood by acquirers of the system, users, developers, testers, and other stakeholders. Unfortunately, the use of natural language to describe complex dynamic systems has severe problems, including ambiguity, inaccuracy, and inconsistency. Many words and phrases have multiple meanings which can be interpreted differently by different people. Therefore, it is critical and essential that the VVT team validates all system requirements for both testability and quality. Evaluating requirement testability. Requirement testability could be defined as the degree to which a requirement is stated in terms that permit establishment of test criteria and performance of tests to determine whether those criteria have been met. This is according to the IEEE Standard Glossary of Software Engineering. Requirement testability is performed by checking each requirement individually for testability in order to create the requirements verification matrix, and later to proceed to test planning, design, and execution of system testing. Evaluating requirements for testability. Researchers suggest that the following attributes may be used as an indicative test for this purpose. Operability. Attributes of a system related to its ability to operate satisfactorily under both normal and slightly abnormal conditions, which are different from the nominal design conditions. Controllability. Attributes of a system related to the ability of an external user to affect system elements in its entire configuration space using only external inputs. One possible example is to compel the system to shift into a desired state or to produce a required output. Observability. Observability is a measure of how well the internal states of a system can be inferred by knowledge of its external outputs. This means that from the system's outputs, it is possible to determine the behavior of the entire system. Decomposability. Attributes of a system related to its ability to be broken into components or basic elements. Stability. Stability refers to the capability of a system to behave in accordance with expected rules. In other words, a stable system is one where for any given initial state and a specified sequence of inputs will always behave in the same way and produce the same expected sequence of outputs. Understandability. Attribute of a requirement where the information provided by it is such that a person with a reasonable knowledge of the subject matter and a willingness to study it with appropriate diligence will be capable of perceiving its significance. Simplicity. Simplicity is an attribute of a system related to the burden it puts on someone trying to understand it. Something which is easy to understand or explain is simple, in contrast to something complicated. The slide is showing an example of a requirement testability matrix. Evaluating requirements quality by attributes. The objectives of evaluating requirement quality are to analyze the quality characteristics of each requirement. Good requirements should be organized and written so that the information is readily understandable to developers, test engineers, customers, as well as all other stakeholders. Traceable. Each requirement should first have a unique identifier. In addition, it must be traceable to one or more higher-level documents, such as user's request for proposal. Understandable. Each requirement must be clearly understood by the implementers and testers of the systems, as well as by the customers and users and operators of the system. Precise. The bounds of the requirement should be evident and unambiguous. In particular, in the case of numerical bounds, it ought to be evident whether the endpoints are included or not. Succinct. Requirements should consist of only the necessary information, without additional details and arguments. Clear. Natural language lends itself to an infinite number of ways to state requirements. Sometimes specifications are stated in ways that may be being clear to some engineers or end users. Non-compounded. A compounded requirement is characterized by having multiple sub-requirements folded into a single requirement. Correct. A correct requirement must reflect true wishes of the customer. This is not as easy as it sounds. Often, different customers or stakeholders have different wishes. Sometimes the customer changes his or her perception about the system and so forth. Nevertheless, the most common mistake is an incorrect interpretation of customer wishes. Complete. A requirement should be complete and give all relevant information on what is required. Consistent. Different requirements should agree with each other. In other words, one requirement should not specify something that it is in conflict with other requirement. Unambiguous. An unambiguous requirement must be precise and must have one and only one interpretation. Feasible. Feasible means the requirement has a sound physical and economic basis. That is, there is a known way to accomplish the stated requirement. Here is an example of a requirement quality matrix. Every system and every requirement is tested and analyzed in order to detect if every attribute is met or not.
Failure Mode Effect Analysis, or FMEA. FMEA is a bottom-up procedure for analysis of potential failure modes within a system or a process and then determining how to eliminate such problems. This is accomplished by 1. Identifying potential types of problems that may occur, their causes, and potential frequency. 2. Estimating the effects of such failures should they occur. 3. Determine how such events may be detected and/or prevented. And 4. Corrective actions, priority, modifying the design or the system manufacturing process. FMEA is widely used in various phases of the product life cycle, especially during the design and manufacturing of systems and their corresponding processes. Some basic FMEA terms. Failure mode. Identify potential types of problems that may occur, their causes, and potential frequency. Failure cause. What was the cause of the failure or the cause which may initiate a process leading to the failure? Failure effects. The immediate consequences of a failure on operation, function, or functionality or status of the system at hand. Failure severity. The consequences of a failure mode. Worst potential types of failures are 1. The degree of injury, 2. Property damage, 3. System damage. The ultimate purpose of FMEA is to take actions to eliminate or reduce potential future failures. Basic types of FMEAs. There are 4 basic FMEAs. 1. Design, which is performed during the design phase. 2. Functional, which focuses on the intended function or use of a system. 3. System FMEA is used to analyze a system at any level from component to system level. And 4. Process, which is performed on manufacturing processes, however, can also be used on engineering processes. Implementing FMEA. There are 5 steps to implementing FMEA. Step 0. FMEA preparation. Describe the system and its functions, or the process that must undergo FMEA evaluations. Create a system block diagram. Overview of major components, process steps, and how they are related. Step 1. FMEA severity determination S. We determine all potential failure modes based on the functional requirements of the system and their effects. Step 2. FMEA occurrence determination O. cause of a failure and frequency which it may occur. Step 3. FMEA, detection determination by design control, D. D represents the ability to detect a system failure or failure mode by means of a planned set of tests and inspections. Step 4. Computing risk priority number, RPN. RPN is calculated by multiplying the severity rating times the occurrence rating times the detection rating. Tables 411, 412, and 413 of the text should be referenced for rating classification.
Expert team reviews. Expert team review is the generic term for the following practices, all of which are considered to be carried out in similar ways. Inspection. Review process that is characterized by examining documents as well as collecting various metrics about the inspection process itself. Walkthroughs. Creator of the evaluated object present it to a group and then analyze it sequentially in hopes to recognize errors, coding bugs, or potential performance problems. This process is less effective. Audits. Use sampling of actual process performance to determine if an organization is actually following prescribed practices or the practices they claim to be following. Peer reviews are usually peers of the responsible engineer or author. Its primary purpose is to achieve open and honest reviews by protecting the responsible engineer for being threatened. Peers may carry out inspections, walkthroughs, or even audits. Document inspections and inspections. Inspection planning. Plans inspection and selects inspection team. Initial meeting. Author explains the document and software code to the inspection team. Inspection preparation. Each inspector examines document and software listing to identify possible defects. Inspection meeting. Document or software listing is discussed. The inspector points of defects for every section. Meeting ends with writing of an action plan. Product correction. Author makes changes in accordance with the action plan. Inspection follow-up. Inspectors make sure problems have been eliminated by checking changes made by author. Defect detection process. Expected to find most of the existing defects in a document. Defect prevention process. Achieves greater benefits by teaching engineers how to improve their grading as they go through the defect prevention process. Optimizing document inspection process and system inspections. The following are some tips about how to conduct and optimize the document inspection process. Establishing inspection purposes, choosing where products intelligently, focusing on finding major defects, applying good inspection practice, providing adequate training and follow-up, publicizing inspection results and statistics, continuously improving inspection process, system inspections. System inspections may be characterized as any task undertaken to determine the condition of a system. Sometimes the determination of labor, materials, and tools and equipment required to repair the system is an organic part of the system's inspection process. Guide for inspection of quality systems and processes. This guide focuses on a top-down approach in order to address organizations' quality products and processes from a system point of view. The following figure shows the 7 components of the quality systems and processes. Key quality systems elements. For each quality element, one first determines if the firm has defined and documented the requirements for the element by looking at procedures and policies. Then, continue looking at both raw and process data to determine if the firm is meeting its own procedures and policies and if its program for executing the requirements is adequate. The following elements are key basic foundation to a firm quality system. Management control. The purpose of management control is to provide adequate resources for system design, manufacturing, quality assurance, distribution, installation, and servicing activities, assure the quality system is functioning properly, monitor the quality system, and make necessary adjustments. Design controls. The purpose of design control quality element is to control the design process to assure that the system meets users' needs, intended users, and specified requirements. Corrective and preventive actions. The general purpose of corrective and preventive actions is to collect information, analyze information, identify and investigate product and quality problems, and take appropriate and effective corrective or preventive actions to prevent their recurrence. Production and process controls. The purpose of production and process control is to manufacture systems and products that meet specifications, developing processes that adequate to produce systems or products that meet specifications, validating those processes, and monitoring and controlling the processes are all steps that help assure the result will be systems that meet specifications. Corrective and preventive actions. Verifying or validating corrective and preventive actions, as well as communicating such activities and providing relevant information for management review and documenting those activities are all essential. Malfunction product reporting. The purpose is to ensure the identification, investigation, and reporting of all malfunction information related to a firm's products and system. System corrective and removals. The purpose is to ensure that the manufacturers and importers of products and systems notify the public or appropriate authorities of any product or system corrections or removal initiated to reduce a risk to the public. System tracking. The purpose is to ensure that manufacturers or importers of a products and systems expeditiously locate and remove defective systems from the market or notify appropriate authorities and the public of significant system problems. Formal technical reviews. A formal technical review is used to evaluate the quality of a system at various points throughout its life cycle. The role is to bring together the most relevant people to criticize the work done, solve open issues, and decide on those action items. In addition, the formal technical review assures timely and effective attention to the technical interpretation of contract requirements and monitors program progress at risk. It also evaluates the validity and completeness of technical documentation in order to assess the maturity of the development effort. Typical formal technical reviews, audits, and advantages of formal technical reviews. Formal system technical reviews and audits are performed during different phases of the system's lifecycle. The most common can be seen from table below. Advantages of formal technical reviews. Formal technical reviews help identify problematic issues earlier and economically than they will be through testing or field use. Formal reviews are a mechanism to make a major system decision. It has a key role in project management because management, quality, and financial issues are naturally intervened with technical considerations. Formal reviews facilitate information exchange. General process of formal technical reviews. The following steps are procedures oriented for engineering systems formal reviews. Entry evaluation step 0. Entry evaluation is expected to use a standard checklist of entry criteria to ensure that optimum conditions shall exist for successful review. Management preparation. Step 1. Ensures that the review will appropriately resource with staff, time, materials, and tools, and conducted accordingly to policies, standards, and other relevant criteria. Planning. Step 2. Identifies and confirms the objectives of the review. Overview of review procedures. Step 3. Ensures all reviewers understand goals and procedures. Individual preparation. Step 4. Prepares for group examination of work under review. Conducting review. Step 5. Meet to pool the results of their preparation activity and arrive at a consensus regarding the status of the system. Rework follow-up. Step 6. Person responsible for the reviewed objectives takes action that are necessary in satisfying requirements agreed at the review meeting. Exit evaluation, step 7. Verifies all activities necessary for successful review. VVT activities, peer review. The VVT leader should prepare for a formal technical reviews of the following steps. Collect results of activities. The VVT team must collect all relevant VVT data from leaders before review. Prepare material for review. The VVT has to prepare with the help of the project team. Analyze material. The VVT team must analyze all VVT related data and provide synthesis to the reviewers. Create review package. The VVT team leader must provide all VVT related material for the creation of the review package. During review, team leaders should contribute VVT related input and be involved in technical reviews along the following lines: review meeting agenda, review project and system status, review technical items, review open issues and actions list, discussions, pass or fail. Pause review. At the end of a formal technical review, the leader should create minutes of the review, recording decisions and agreements along with follow-up action items. The final report should be complete and distributed and include meeting minutes, an action item list, a review of score results and the scoring system level, and lessons learned. Guidance for technical reviews. Clear and predefined objectives and a clear statement of purpose. Conduct meaningful internal reviews. Not too early and not too late. Pay careful attention. Select proper reviewers. Review team must be compromised. Reviewers should perform certain tasks. Reviewers should educate participants and project team. Management support. Constructive criticism. Customers are active participants.
Group evaluation and decision is based on a group's evaluation and decision meeting. Is active throughout the entire system life cycle, follows technical reviews, has a distinct advantage. Group evaluation and decision process. Phase 1, defining issues at hand. Phase 2, making a decision. Phase 3, implementing and evaluating the decision. Factors in group processes. Individual and group skills, cognitive mechanisms, communication dynamics, decision policies, task complexity, social factors, environmental influences. Leaders of evaluation and decision groups may be characterized into the following decision-making styles. Aristocrat. Leaders tend to solve problems on their own based on information available to them at the time. Consultative. Tend to share problem solving with members of the group. Participative. Leaders discuss the problem with the members of the group, and together the leaders and members devise an appropriate solution. Group process risk. Group evaluation and decision processes are not always successful. If derived solutions and appropriate mitigating solutions are not timely, the group process may be a failure. In addition, sometimes the group makes a bad decision. Among causes that may be to blame for a bad decision is bias in sharing information, cognitive limitations, group polarization, and most notoriously, group thinking phenomena, as well as plain old social loafing. The following figure describes specific group evaluation and decision methods.